All right, so there we go. Conic sections. Um, you know, when a plane intersects a double cone in one of three ways. Let's start with parabolas. One of the classics. All right, so here's our definition of a parabola. A parabola is the set of points in a plane that are equidistant from a fixed point, F, which we call the focus, and a fixed line called the directrix. And so I can illustrate that in this figure. And it's a set of all points that are equidistant. So they don't have to be the same distance from the point and the line. But what we're saying is that any point on the parabola has the same distance to the focus as it does to the directrix. So here's another point on the parabola, same distance to this line as to that point. Remember, we always measure the distance from a point to the line as the perpendicular line that connects them. So these are right angles, right? And so if you look at the set of all those points that satisfy that definition, that gives us a parabola. The parabola is important in obviously orbits, as I just described, but also things like optics and information. So optics like a flashlight. So the inner piece of the flashlight is a parabola, and the light bulb will be placed at the focus. And so the way it works is all light that's reflected out of the focus will actually reflect in a straight line like this, outwards. So that's why a flashlight works, because this is a reflective surface, right? And you have your light bulb at the focus, and it reflects all the light directly out of it, like that. And that's also the way a satellite works, the opposite. That's why you have that little node on the inside of a satellite, because the information is beamed in from space, and all that information will be reflected directly towards the focus, which is where you have your receiver of your satellite. So parabolas, important in society. All right, so the point halfway between the focus and the directrix is called the vertex. So that's that guy right there. And the line through the focus perpendicular to the directrix is called the axis of the parabola. So I'm talking about this guy. So in the 16th century, Galileo showed the path of a projectile is parabolic, which you guys did an entire junior year project on. I'm sure you're familiar with projectiles in motion. All right, let me make sure. Okay. So we're going to create our equation of a parabola by setting the vertex at the origin. And then we're going to explore a particular point, xy, that lies on the parabola. So we just chose some random point xy. And we're going to call the focus has coordinate 0, p. And that means by definition, the directrix has to be at y equals negative p. And so all we want to do is create an equation that relates y and x. And so we're going to use some basic sort of algebraic geometry formulas that we already know from your earlier years in secondary school. Good Lord. All right, here we go. So the first thing I want is the distance between P and F. You guys remember the distance formula?
Basically just Pythag, but square root.
It is just Pythag, right? So if I'm looking for the, yeah, you're right. So if I'm looking for the distance between P and F, we can think of Pythag in terms of this triangle here, right? And so we're looking for this side of the triangle. Right, that's PF. So I know that PF squared equals, now this side squared, how do you find the horizontal distance between 2 points? This is 0, right? And this is just x. So what's that horizontal distance? Yeah. So that's just x. PF squared equals x squared plus, now I need this distance. I need the vertical distance, which to find the vertical distance between 2 points, this is y, right? And this is p. And so wouldn't you just do top minus bottom? So y minus p. So that distance is y minus p. And so by Pythag, pf squared equals x squared plus y minus p squared. And then if I just want pf, pf is the square root of x squared plus y minus p squared. Right? Well, by definition of any point on the parabola, the distance from the focus to that point, which is what we just found, has to be equal to the distance from the directrix to that point, which is this, right? All right, so that means the square root of x squared plus y minus p squared has to equal, all right, so now let's come up with an algebraic expression for that. Well, again, to find the vertical distance between any 2 points, you just subtract the top y value minus the bottom y value. The top y value here is y. This y value is negative p. So what's this total distance? Yeah, y minus negative p, which is just y plus p, right? All right, so that square root has to just equal y plus p. All right, well, now we have an expression that relate x and y. Because remember, p is just some fixed constant. But usually when we look at functions, we like to look at them in terms of y as a function of x. So let's just do a little algebra and isolate y. So I'm going to square both sides. We get x squared plus y minus p squared equals y plus p squared. All right, let's expand these. So plus y squared minus 2yp plus p squared equals y squared plus 2yp plus p squared. All right. A couple things will cancel here. P squared, those are gone. Y squared, those are gone. I can add 2yp to both sides. And I end up with x squared equals 4yp. This isn't necessarily the way you're used to seeing the equation of a parabola, right? So we can solve it in that way. So this is y equals 1 over 4p times x squared. Or I could rewrite that as y equals ax squared. That's probably a little bit more normal looking for a parabola. And we'll just say where a equals 1 over 4p. Remember that p, in this case, is the fixed y coordinate of your focus. So there we go. We built a parabola, the equation of a parabola from the ground up, just from the definition of what it is, right? All set of points that are equidistant from a fixed point, which we call the focus, and a fixed line that we call the directrix.
Is it important for us to know how to derive this? Like, should I have written all this down, or is the most important part just a equals 1 over 4p?
Yeah, that's important. I mean, the equation at the end is going to be the most important, but understanding what the focus and the directrix are is also important. I'm not going to ask you.
Okay.
I'm not going to ask you to rederive the parabola. All right, but this is really only for a vertically opening parabola, right? So things get kind of swapped around for a horizontally open. I'm not going to rederive it because it's the exact same process. You're just going to kind of swap x and y. And then, yeah, this is what I just told you, right? A equals 1 over 4p. And then we can have the standard equation y equals ax squared. All right, so that's for this case. If we change it to a sideways opening parabola, we basically just swap x and y. So y squared equals 4px. All right. One important thing to write down, and I'll go back for the other one. If p is greater than 0, the parabola is going to open to the right. And if p is less than 0, it'll open to the left. But this is already the same reasoning, right? So if p is greater than 0, then a is going to be greater than 0, and you're already used to that, knowing that, right? If the coefficient is positive, it opens up. If the coefficient is negative, it opens down. This is the same thing, but with p. Yeah, so if p is positive, it opens up. If p is negative, it's going to open down. All right, let's do an example. Find the focus and the directrix of the parabola, y squared plus 10x equals 0, and sketch the graph. All right. So we're going to put it in that form that I gave to you guys in the blue box, just because that's the easiest form to identify what P is. But right away, you should notice, since y is the variable that's squared, this is going to be a sideways opening parabola, right? So I'm just going to put it in that form, y squared equals negative 10x. Then going back and just looking at this formula, that means my 4p is equal to negative 10x. And that means that, oh, I'm sorry, just negative 10, not negative 10x. 4p equals negative 10. So p equals negative 10 over 4, which is negative 2.5. In a sideways opening parabola, p is the x coordinate, right? So that means that my focus will be at negative 2.5, 0. My directrix is going to be a vertical line since it's sideways opening. And it'll be at y equals positive 2. No, x equals positive 2.5. Apologies.
Can you explain how you got to the directrix again? Just like, because I understand the whole process to get the focus and the negative 2.5. So how did you get x equals 2.5 for the? Oh, is it just is it just because it's the
opposite of p?
Oh, okay. Oh, okay. Okay. Thanks.
If it's vertically, or if it's horizontally opening, it's x equals the opposite of p. If it's vertically opening, it's y equals the opposite of p. Yes. So here's like a little visual of what's going on with the parabola, right? You can see those points stay equidistant as, or sorry, those distances stay equidistant, PF and PM, as we trace out those points. What I wanted to be able to do was stop. I want to be able to move. This won't let me. Oh, there we go. All right, so what do you think happens? Sorry, guys, I'm not sharing the right screen with these other people. What do you think happens with this, with the parabola, the shape of the parabola, as the focus and the directrix get closer together? Basically, either going to get wider or skinnier. Which way is that going to go? Yeah. And if you put them on top of each other, it becomes, right, it degenerates to a single point, basically. And then as you move them away from each other, the parabola gets wider. So you can kind of see that here. Yeah, this isn't, I'm sorry, I'm not showing you the one that we just graphed, that we just found. But I'll graph that one in a second. I just wanted to show you the basic idea. as we move the focus away from the directrix, you're going to get a wider parabola. As you move it closer, you get a skinnier parabola. As you let the distance between them approach infinity, the parabola will basically approach a vertical line in this case, right? And as you let them approach being on top of each other, the parabola will degenerate to a single point once they're on top of each other. All right. But ours, that is not ours. Ours should look like, it should be open in the left because P is negative. Let's draw our coordinate plane. We have a directrix at 2.5. So here's my directrix. We have a focus at the coordinate 0, 2.5. Or I'm sorry, negative 2.50. And then the parabola itself. The vertex is going to be halfway between those, so it's going to be, in our case, right at the origin, right? And it opens away from the directrix and around the focus. So I don't care for you to find any more points on the parabola. You can just sketch it at this point. But just know that the further apart the focus and the directrix are, the wider the parabola will get, and the closer together they are, the skinnier it will be. Sorry. All right, we good? Ellipses. These guys. 1, 2, 3. Just kidding. Those are ellipses. Not the same thing. All right, so let's first define what an ellipse is as a set of points. So it's the set of points on a plane whose the sum of whose distances from two fixed points is a constant. All right, cool. So, hold on. All right, sort of illustrate what I'm talking about. An easy way to think about this is if you looped a piece of string and pinned down 2 points and then pulled it taut. So to keep the sum, like the sum of that string is not going to change length ever, right? In total. But the individual lengths, like the distance from one of them to a pin, may change. The total string length won't change. And so if I then keep the string taut and trace around, come on now. So you can see those sums are changing. Oh, shoot, I'm sorry, I'm not sharing this again. You can see those sums are changing, but the individual distances are changing, but the sum remains 7.6. That's going to trace out an ellipse. So the sum remains constant, even though the individual distances from the tip of the pencil to the pin may change. And that's the definition of ellipse. The closer those two foci get together, what sort of a shape do you think I'm going to get if I move them closer? More circular. When I move them right on top of each other, I get a perfect circle. Thus, a circle is just a very special case of an ellipse, right? All right. Now we have like the general idea of what an ellipse is. Let's deal with the algebraic geometry of the ellipse. So here's how we're going to set up our diagram. We're going to center our ellipse at the origin. We're going to take a generic point on the ellipse to be xy. We're going to have focus 1 at negative c0, so negative c is a fixed constant, and that puts focus 2 at positive c0. And one more thing, we're going to define the length of the major axis, so this distance. That's going to be 2a. All right, so one thing I want to make a note of is that the distance p to f1 plus the distance p to f2, that has to equal 2a. And that might not be immediately obvious. I'll show you why. Remember that the sum of those two distances is the same no matter where we are on the ellipse. So think about if we are at the endpoint here, if that's point P, then this is the distance P to F1, and this is the distance P to F2 from here to here. And notice if I add those together, I overlapped this little section twice, which is going to be the same as that distance, right? And so that's the distance all the way across the major axis, which is 2a. All right. So using that, we can now get this in terms of x and y, because we can come up with the distance from P to F1 and P to F2 just by using the distance formula. Remember, distance formula is really just a special case of Pythag. And just to remind you, just so that we don't have to use Pythag to redevelop it every time, it really just comes out to x2 minus x1 squared plus y2 minus y1 squared under the square root. And that's the distance between any just two coordinate points. All right, so the distance from P to F1 is just going to be x minus negative c squared. So it's going to be the square root of x plus c squared. And then y minus 0 squared. So that's just y squared. And then same thing, P to F2 using the distance formula, that's going to be plus the square root of, that's going to be x minus c squared. And then that's still going to be y squared. And that's all equal to 2a. All right. Well, I like to do the first one. I like to go all the way through the algebra of developing the equation of a parabola. This one gets a little dirtier. I mean, you guys are completely capable of doing it. It's just algebra, but what we're going to have to do to get rid of those square roots is square both sides, and that's going to get a little messy when we have to square that left side. So you don't have to write this down, but I'm just going to walk you quickly through it. All right. So that's second line is where we got to, right? Right here. So what we do is then subtract one of the square roots to the other side to be with the 2a, and then we're going to square both sides. That's where it gets a little messy. So this whole thing is actually a one-line equation with a ton of terms, right? So you can just trust me on that algebra. Take that, combine like terms, get rid of things that cancel on both sides, and we simplify to this. But then we got to square it again to get rid of that second square root. And so that's going to involve squaring out this side, which still gets a little more messy. And that simplifies to that. So now we've gotten rid of the square roots at least. And again, I'm not going to make you derive these again. And it is just, what is this? Taskbar just switches sides on me at random points throughout the day. All right. And then again, combining like terms and simplifying, we get this. So we have a squared minus c squared quantity times x squared plus a squared y squared equals a squared times quantity a squared minus c squared. All right, well, what we're going to do, remember that a and c are fixed constants. So what we're going to end up doing is dividing out all of a squared minus c squared from the entire equation. Let me actually write out what that would look like. So that would look like this. If I divide out a squared minus c squared, I end up with x squared plus y squared over let's see, that would be a squared minus c squared over a squared equals a squared. So just remember that if I take y squared and I divide by this, I would flip this and multiply. And that would get me back to here. All right, and then if we divide a squared out from everything, I end up with a situation that is going to be equal to, one more time, x squared over a squared plus y squared over a squared minus c squared equals 1. And if we let a squared minus c squared equal b squared, we actually end up with what we know to be our ellipse equation, which is this. And so you can see they let b squared equal a squared minus c squared, and we end up with a nice, simpler, much simpler equation. X squared over a squared plus y squared over b squared equals 1. One important thing to note is that it actually turns out that b is the distance from the center to the vertex of the minor axis. So a is the distance from the center to a vertex of the major axis, b is the distance from the center to the vertex of the minor axis, and c is the distance from the center to a focus. All right, so let's get main points here for an ellipse. We call the bigger axis the major axis. We call the smaller axis the minor axis. And so here we go. This is a horizontally opening ellipse. It will take the form x squared over a squared plus y squared over b squared, where specifically a is bigger than b. It will have foci plus or minus c comma 0, where c squared has the relationship a squared minus b squared. How's the off-campus lunch? Long, dude. I had lunch duty yesterday. It's gonna be a long time when it gets hot out. I mean, we're gonna have to eat it. I think they're just crossing their fingers that, like.
And she said that if like there's a day where there's an extreme heat warming, then they might just help things like. But she also said that there hasn't been an extreme heat warming in May for the last like 3 years.
Yeah. I would imagine they're like crossing their fingers that the cases keep plummeting.
Oh yeah. So
yeah, especially now that they're opening vaccines up to everybody. All right. So just like the hyperbola, we need to deal with the case where the ellipse could go the other way, so it could be vertical. And so we just swap x and y in that case. And now the foci lie on the vertical axis, and that's the major axis. The horizontal axis is the minor axis, but the relationships stay the same. So notice that all that happened there was a squared and b squared are swapped, so that x squared is over the smaller value, because b is less than a, right? Everything else stays the same, except the foci are now 0 plus or minus c because they fall on the y-axis. All right, now all we got left is a ellipse example. No calculus, same idea as the parabola example. All right, so it says sketch the graph of 9x squared plus 16y squared equals 144 and locate the foci. So what we want to do is just try and get this into a standard form that we're used to. So we'd like to get it to look like x squared over b squared plus y squared over a squared equals 1, or x squared over a squared plus y squared over b squared equals 1. Either way, we want it equal to 1. So all we're going to do here is divide out the 144 from everything. And so another way to write this is that's x squared over 144 over 9 plus y squared over 144 over 16 equals 1. If that confused you, just remember to simplify those, I would flip the denominator and multiply, and I'd be back to what I have in that first line up there, right? But the nice thing about this is actually 144 over 9 reduces neatly. 144 divided by 9 is 16. So this is really just x squared over 16 plus y squared over, that means 144 divided by 16 is going to be 9 equals 1. All right, so right there you should be able to tell me what type of ellipse this is. Is it going to be a horizontal ellipse or is it going to be a vertical ellipse? An easy way to remember is what's the bigger denominator under? What variable is the bigger denominator under? It is a, but in this case, looking up here, what variable is the bigger denominator underneath? X. So it's horizontal. If the bigger denominator is under y, it's vertical. All right, so remember that these denominators are a squared and b squared respectively. So from that, I can tell that a squared is 16, so a is 4, right? From this, I can tell that b squared is 9, so b is 3. And remember, those are just the distances from the center to a vertex of the major and the minor axis, respectively. So in this case, to graph this, I'm going to start at 0. I'm going to go out 4 in the x direction. 1, 2, 3, 4. I'm going to put a point. Do the same on the other side. 1, 2, 3, 4. Put a point. I'm going to go up b and down b. 1, 2, 3. There's a point. 2, 3. There's a point. And now, just before I finish graphing, let's find our foci. Well, we know that c squared equals a squared minus b squared. So in this case, c squared equals 16 minus 9. C squared equals 7. C is the square root of 7. Which is what? Somewhere between 2 and 3. 2 squared is 4, 3 squared is 9. So a little closer to 3. That means my foci, since they're on the x-axis, will have coordinates plus or minus root 7, comma 0, right? And so I'll just graph those. So my foci will be closer to 3 than to 2 on the x-axis, like that. And then to graph it, just draw your ellipse. Just do your best to kind of connect those 4 vertices in an ellipse. Don't be mad if yours isn't a picture-perfect ellipse like mine is. Had years of practice.
One side is perfect, the other side is like super pointy.
I've been doing this for 15 years. I still can't graph it. Oh!
Like a teardrop.
It does it for parabolas too.
Oh, that's awesome.
Like all of them are very even. I love it.
Anyhow, there we go. We got our foci. We got our ellipse. We're all set. All right, so here's your part 1 problem set. It's just problems that have to do with parabolas and ellipses. You can get started with that. Next time we're going to do hyperbolas. Zoom, any questions for me?
Nope. When you have office hours on Thursdays, correct?
Tuesdays, Thursdays, and Fridays.
Epic.
All right. Well, you guys can log off and get started if you wish. You guys can't. You have to stay logged in here physically. Woo. It's a lot.
First day back from spring break.
Hey, count 2. You know what you signed up for.
I don't regret sending
Yeah. Plus, you get all types of class time to do.
Yeah. What's the cost? Small for the
Yeah, it's nice. You are.
I don't know. People, like, they have like money to keep having all these tests, and I'm pretty good.
How's day 2 felt? Any more normal? Yeah.
I honestly missed it. I didn't realize how much I missed it.
Yeah.
My extrovertness is thriving. I have people to talk to.
I know, being able to talk to people.
Because there's so many people at school that I don't talk to unless I'm in school.
Right.
But people that wouldn't bother to like
Reach out.
reach out to, exactly.
I talked to like 4 people. So you guys
Text, I guess, but like, I don't know.
What are you doing, right, dude?
I just want to remind you that you have been shaming me for getting the wrong computer.
Well,
You
the last like
you
month.
get the wrong
no,
computer?
no, you got the Intel version. I get on the MacBook
I get the
Pro.
wrong
Oh, I
processor.
have the same one.
No,
Wait,
right?
no, use the bar. Use
Get the
the
bar.
fancy bar.
Okay, see, the Intel version is in here in all
What's the
categories.
other version? Like the big one?
No, the
No.
other one.
No, now they have the Apple chip, don't
The
they?
Apple Silicon chip.
The what?
The Apple. Okay, so your phone runs a processor.